Hello everybody, welcome to Blue Marble Science. The other day Quantum Eraser had a debut show where he and Nathan and Sleepy and the rest of them completely confused themselves and everyone else about helicopters and how they behave in our atmosphere. Now I don't really care if they're confused, but I hate for them to confuse the rest of you. So let's see if we can sort this out. Warning. As usual, severe facial and monitor damage alert is in effect. Get out those oven mitts. Push the monitor back out of punching range. And Gladys, let's light this dumpster fire and have some fun.
And I want to bring this point up here. And Nathan brought it up yesterday on the show, and it seemed to go without comment. And I caught it right away. And it was his point that, and it had to do with the Coriolis effect, about the conservation of momentum. And when a helicopter takes off and hovers, most of the Baltard argument is, well, conservation of momentum of the helicopter. But he made a brilliant point. What is, if the helicopter starts to rise in elevation, then it not only must conserve the momentum, it must increase the momentum. That's what I'm talking about. Being able to think on your feet. And I thought it was brilliant, actually. And he's absolutely correct. I want to hear the answer to that argument.
Hold on there, Quantum Dum Dum. Let's make sure everybody understands what you're saying. You're telling us that if our idiot Cletus here watches his buddy take off in his helicopter, the helicopter's height above the surface increases the radius and therefore the circumference. So the helicopter is no longer going to be able to stay over a point on the Earth. It will just simply go whizzing off in some direction or the other. Is that pretty much it?
There is no answer to that argument. You've got to increase velocity, match the tangential speed that they say the Earth is moving at, in order for them to defy the proof of globe Earth spinning that is Coriolis effect. So this is an argument that the helicopter takes off and retains the tangential velocity of the Earth spinning beneath it. Well, okay, an inch above the ground, apparently it's retained the velocity because the Earth and atmosphere travel as one, not giving you any deviation that's supposed to prove the Earth spins. Okay, that's where we're at with this. Not a proof of globe Earth spinning, not a proof of deviation, not a demonstration of Coriolis effect. Okay, they're traveling as one. This is an explanation for why what we see in reality is a helicopter can hover. Okay.
I'm not sure why you act all shocked and amazed, Nathan. The Earth is covered with lots of stuff that looks like this. Really big mountains, lots of trees, waves on the ocean, just the friction of the surface of the Earth as it spins. That friction is what causes the atmosphere to rotate. Once it is rotating, there's nothing to stop it. What the heck is up there? Nothing. A few birds, a couple of airplanes. None of that stuff's going to slow the atmosphere down. It's just going to keep turning exactly like the Earth rotates.
Then it goes up much, much higher. Now, in a reified sphere model, that means it's further out towards the edge, like you moving out towards a further outside point of a roundabout. Therefore, you're moving faster on that outside edge. Well, if the helicopter's getting further away from the central point of rotation, then it's going to have to go faster to keep up with the tangential velocity of the Earth spinning beneath it. It's going to have to actually increase speed. They're saying, oh, well, it retains the speed. Well, what about the fact that as it goes up, it would have to increase speed in order to maintain its position above the ground that it left?
Well, at this point, we're making a mountain out of a molehill. If we calculate the speed at the equator of the Earth, the rotational speed is about 1,037.5 miles per hour. If we go up 1 mile in height, 5,280 feet, the speed increases by 0.3 of a mile per hour to 1037.8. If we go all the way up to 21,120 feet, that's 4 miles, the speed has increased to 1,038.6 miles per hour. That is a 1.1 mile per hour difference. That's all. But Nathan is leaving out one important fact here, and that is these speeds that are being shown are the speeds of the atmosphere, neglecting any form of wind. The airplane or helicopter is going to be simply carried along with the winds aloft. It is not a ballistic device. And a 1.1 mile per hour change in speed is so insignificant it's ridiculous to even talk about. Let me show you why. The reason this argument is complete foolishness is just this. This is the Aviation Weather Center. You can pull this up at aviationweather.gov. These are the winds and temperature forecasts for the current period. I've got this thing set for an altitude of 18,000 feet, flight level 180. This is the wind chart, and the way you read this, these are like arrows, and these are like the feathers on the arrow. A long line means 10 knots, a short line means 5 knots, and a triangle means 50 knots. At 18,000 feet today, here's 30 knot winds, here's a 50 knot wind, there's 40 knots. Clearly, 1.1 miles per hour is totally insignificant compared to the normal winds you expect to see, especially when you get into the flight levels. Notice one other thing too, though. Notice how these arrows in this location are headed in the northeasterly direction. As we go a little further up, they continue turning and back toward the west. Over here, they're headed down south, and they're going in a circle. They are rotating counterclockwise. Why? Because there's an upper level low today right in this region, and that's causing that rotation. That is the Coriolis effect.
So it's an absolute impossibility unless it can, increase velocity. It just can't. I can't see any way of squaring that circle in their argument. Maybe they'll come back to something QE, but I honestly can't see them squaring that circle.
I can't wait. I'm going to push it.
I'm just going to do a bit of maths on that, guys, actually. I was just thinking about that. The argument they'll have is that the differential of 30,000 feet is insignificant in terms of the increase in the circumference, and then therefore the angular travel that you create on the two planes. They're going to make out, but the reality is it is applicable, measurable, and demonstrable. Irrespective, I'll do some maths on it in a minute. But
yeah, it doesn't matter. It's a qualitative.
9 kilometers, isn't it?
Yeah, it's
so instead of a radius of 6731, you're going to have a radius of 6740. So you're going to have an increased radius of only 9 kilometers. So technically, it's going to be minimal in terms of the altitude thing, but technically, it should be demonstrable.
No, this wouldn't be demonstrable, and I just showed you why. The winds aloft are so much stronger than any 1 mile per hour change in the rotational speed of the atmosphere, it would just be simply lost. The corrections required for the wind would be 5 times, 10 times, 50 times as much. By the way, helicopters don't hover at 30,000 feet. This is one of the most high-performance helicopters on the market, the Augusta AW109. This thing will not hover above 10,400 feet. Helicopters are unpressurized, most of them are. I only know of one that I can think of, and it's extremely large, that has a pressurized cabin. Typically, helicopters don't fly above 10,000 feet. They have no reason to. It's not very comfortable for the passengers, frankly.
Technically, it's and it's not just a single; it's a constant speed differential that you've got to adjust for. So you're constantly having to be going whatever, just call it 1/2 kilometer an hour. You're going to have to be making that constant adjustment in that direction to just hold that position, because you're going to have to add onto the tangential speed, aren't you? So it's going to be a constant movement, and then if you were then to increase slightly, that constant is going to adjust slightly and increase slightly in relation to increasing altitude.
I've got to just must step in here. To achieve what? So you're saying, well, you're saying that's what would be necessitated by their rhetoric of Earth spinning and atmosphere spinning along with it, and you're making these constant adjustments to compensate for the fact that as you raise in altitude, the overall circumference of that you're traveling is increasing in relation to the spinning ball underneath. Therefore, you'd have to increase your velocity in relation to it. That's your argument thus far. Well, at that point, I'm going to say, well, for what? Well, to negate the claim proof that Earth's spinning. So what should happen, according to the globe Earth fundy rhetoric of a spinning ball in a vacuum, is that the helicopter takes off, and because you remain on the spinning reference frame underneath it, you see it drifting. Now, it's not really drifting, it's just ascending vertically. But because you spin underneath, you see it appearing to drift. That's the proof they claim that Earth is spinning. It rotating underneath Earth, that is, and the helicopter just going in a straight line and seeming to you, the observer, to drift.
Nathan, you've got the physics comprehension of a mentally retarded whistle pig. A hovering helicopter is not moving in the rotating frame of reference. It is not experiencing any Coriolis force. What the hell is wrong with you?
Well,
let's just call it like
100 kilometers per hour is what I've just worked out would be the actual, because I said it was going to be minimal. So I've just quickly done it. So based on a 35,000 feet increase, that takes the radius up 9 kilometers. So it goes to 6371, from 6371 to 6740.
Say what? Where did that number come from? 6371 plus 9 is 6740? You're doing Flurf math. You've been talking to Anthony Riley, hadn't you?
So that changes the circumferential differences from 40,000 kilometers to 42.3 thousand kilometers. So to rotate at the rotation speed at 40,000, so on at ground level, is 1,666 kilometers per hour. You then go up those 9 kilometers, the increase turns the tangential speed, as they would have called it, to 1,764, which is a difference of 98 kilometers per hour.
Okay, fellas, let's see if we can get this right. The radius of the Earth is, in fact, 6371 kilometers. If we add 9 to that, it's 6380. Let's figure out the circumferences. 6380 times 2 pi is 40,087 kilometers. 6371 times 2 pi is 40,030 kilometers. The difference is 57 kilometers. That's a speed difference of 2.38 kilometers per hour.
And I'll stand to be corrected because I've just kind of done it on the fly, but that's a lot more significant. I thought that's, 70 mile an hour difference that you've then got to adjust for to pretend that you're hovering. But how do you get a helicopter to go sideways to add or subtract a tangential speed and then maintain its straightness in terms of it looking like it's hovering over the ground? The two would seem incompatible.
They are incompatible, completely incompatible, because the rhetoric that fights against the proof they need that it spins, i.e. the Coriolis deviation, when we're in this situation arguing about why it's not deviating, as we observe, not giving them the globe proof, then they have to increase what they're claiming is a retained velocity. Well, you don't increase something that you've retained. If anything, it would decrease. But it certainly wouldn't increase as you go up in height. That's an impossibility. Absolutely impossible. No, it can't do that. If it's retaining a velocity, it doesn't go up higher and say, I better go a bit quicker. No.
Exactly. And the reason why it's important, Anthony, we discussed this earlier today, is that they try to use the Coriolis effect to prove the Earth spinning. That's why.
We can use Coriolis and other methods to prove the Earth rotates, but we can't use a helicopter. I've just shown you why. The winds aloft are far too strong for that to be an effective method. You won't prove anything. What you can use is a Foucault pendulum. These things go back to the mid-1800s. There are more than 300 of them on the planet operating right now, and they all show the same thing. And there is no other explanation for why the Foucault pendulum behaves the way it does, other than it is moving in a rotating frame of reference. Hey guys, thanks for watching. Hope you enjoyed it. If you did, hit the like and subscribe buttons, and we'll catch you on the next one. Hey Gladys, we're out of here.